Hi, in this presentation we're going to talk about the atomic nature of matter. So about 2,000 years ago, the ancient Greeks noticed that if you had something, you could cut or break it into smaller and smaller pieces. Like chopping up a carrot for your dinner, you can chop it up in smaller pieces. Or like here our rock, we could take a hammer and just keep breaking it down until we have a powder. But eventually, at some point, you're going to get where a piece is so small that you really can't break it down any further. And the ancient Greeks called this atomos, was their word for uncuttable. Not all the ancient Greeks accepted this concept of atomos. Some, such as Aristotle, thought instead that matter was made up of four elements: fire, water, air, and earth, and that everything we see around us is made up of these four elements in different proportions, whether it's a wooden table or a drinking cup or a rock or the flesh of your body is just made up of these four elements in differing proportions. And this theory held sway for several hundred years in Western science. In the early 1800s, a man named John Dalton was looking into the structure of matter, and he kind of rediscovered this concept of atoms, and he refined it and reintroduced this concept of atoms being the building blocks of matter. And then in 1827, there was another scientist named Robert Brown, and he was observing particles under the microscope. And he noticed that some of his particles exhibited this little vibratory motion that he really couldn't explain. They were inanimate particles, so they shouldn't have been moving, but he could see them kind of vibrating when he looked at them under high magnification. And he hypothesized that these vibrations he was seeing were the result of collisions between the visible particles that he could see with his microscope and invisible ones that he could not see. And he called this Brownian motion. And Brownian motion was pretty much a mystery for about the next 100 years until 1905, until Einstein explained Brownian motion as being the result of the movement of tiny atoms, atoms that we can't see, but we can see the result of their collisions in the motion of objects we can see. Atoms are incredibly tiny. If we could take an atom and enlarge it to the size of your body, then your body would be the same size as the average star, which is quite huge. Or look at it this way: say we have this helium atom over here in our picture on the right, and if we said that helium atom was the same size as a tennis ball, then tennis balls would be the size of planet Earth. Atoms are also incredibly numerous. If we took about a gram of water, about a thimbleful of water, and you might not have ever seen a thimble, so that's probably about maybe a quarter of a teaspoon of water. There's 10 to the 23rd power atoms, that's 10 with 23 zeros behind it, atoms in that gram of water. And that's numerically a greater number than all the drops of water in all the lakes and rivers on Earth. So atoms are very, very tiny, and they're incredibly numerous as well. Atoms are always moving as well, even in solid objects that we think don't have any movement, like, say, your coffee cup or the chair you're sitting in or the floor. The atoms are still vibrating in place. They're in solids, they're pretty much held in place, but they can vibrate in place. In liquids, again, now the atoms are less tightly bound and they can move much more freely. And in gases, they can move more freely yet. And gases can move so freely that the atoms in the breath you're exhaling right now can spread around the world in only a few years. And then you'll be breathing in those same atoms again, maybe. Atoms are also ageless. Some of the atoms in your body, especially say hydrogen atoms, are as old as the universe itself. They were created in the Big Bang that created our universe. Other atoms of, say, heavier elements were created in explosions of stars that lived and died before our solar system was even created. So all the molecules of our body basically were either born in the Big Bang or came into being through these ancient stars and supernovas. So atoms are kind of like energy. It's really hard to destroy or create an atom, but they can be reused constantly, recycled. Another interesting fact about atoms is they're mostly empty space. So even like the chair you're sitting on right now is mostly empty space. If we took an atom and we started enlarging them again like we did before, then we blew it up to the size of a cantaloupe or a volleyball. Even if our atom was that large, its nucleus and electrons, its subatomic particles, would still be too small for us to see. Most of that atom would just be the space in between the electron cloud and the nucleus. So let's think about this. The human population of the Earth grows each year. There's more and more people on planet Earth each year. Do you think the mass of the Earth increases each year as well? And the answer to that question is no, it doesn't. There's pretty much the same amount of atoms here on Earth as there were when Earth was first created billions of years ago. We're just recycling those atoms. So if a woman becomes pregnant and her body is going to take atoms from the food she eats and also from her own body tissues to create the body tissues of that fetus. And then as that baby grows and is born, as the baby eats food, it takes atoms from the food it eats to create its body tissues and grows into an adult. So we're not creating mass here. We're just transforming it from one state to another. We're taking the atoms from our food and making our body tissues out of them. So even though the human population of the earth is growing constantly, the mass of the earth is not increasing. Atoms are also too small to be seen with visible light. When we see things, we're basically seeing the reflection of light bouncing off of an object, and our eyes are receiving that reflected light. And if something's smaller than the wavelength of visible light, then of course we're not going to see a reflection off of it, so we can't see it. So this is why we can't see atoms. No matter how strong a microscope we get, if we're using light, we're not going to be able to see that atom. But we can use other devices such as a scanning electron microscope, which does not use light, it uses an electron beam. And the wavelengths of this beam are very tiny, smaller than atoms. So using the scanning electron microscope, we can actually visualize atoms. This picture you see here was taken in 1970 with a scanning electron microscope. And this was the first relatively high resolution image of individual atoms, a picture of thorium atoms. And so scientists were really excited when they could actually see this picture. And it might not look very high def to us, but again, this was the best picture of an atom that had ever been taken at the time. When we look at the structure of atoms, we can see that the atoms have a nucleus that's in the center of the atom, and then they have an electron cloud that surrounds that nucleus. And the nucleus contains most of the atom's mass. And that nucleus is extremely, extremely dense. Now, remember we talked about how tiny it is. But if we could somehow get enough nucleus together and pack them into a lump the size of a pea, okay, like the not even the size of the fingernail on your little finger, it would weigh 100 million tons. That's how extremely dense a nucleus is. And there's strong electrical forces that keep these nuclei apart, which would make it hard for us to pack those nuclei together in the lump. As the nuclei are pushed together, there's very strong electrical repulsive forces that kind of push them apart. So it's really hard to mash two nuclei together. And usually this can only happen under intense pressure or heat. So conditions we might find, say, in the center of the sun or other stars, or in thermonuclear bombs. The nucleus of the atom is composed of nucleons, and there's two different types in the nucleus of the atom. There are neutrons, which have a neutral charge, and then there's protons, which have a positive charge. And you can see in this picture of a carbon atom, we have 6 protons, that's what tells us it's carbon, and 6 neutrons in the nucleus. Surrounding the nucleus in kind of a cloud are our electrons, which have a negative charge. And you can see in this picture, this atom has 6 negatively charged electrons. So we can see if it has 6 protons and 6 electrons, the atom itself is going to have a neutral charge. So we saw in the picture on the previous slide that a carbon atom, for example, has 6 protons in its nucleus. And you might have been saying, well, wait a minute, back when I was learning about electrostatics, I was taught that if you have 2 positive charges, they're going to push each other apart. They're going to repel. So why are these protons hanging out together? Why aren't the protons in the nucleus of this carbon atom pushing each other apart? And the answer is the strong nuclear force. Think back to last week in the gravity presentation when I talked about the 4 fundamental forces. And those 4 fundamental forces are gravity, the electrostatic force, the strong nuclear force, and the weak nuclear force. And we learned that gravity, of course, is the weakest of those. But let's look at this picture here. And we have on the left, labeled A, we have 2 protons which are very close together. And over on the right, we have 2 protons that are very far apart. When 2 protons are very close together, there's a couple of forces that are acting on them. There is our electrical force, which is going to tell us, hey, these 2 positive charges want to repel each other. And there's also the strong nuclear force, which is much stronger over these very small distances. So the closer the protons get, the stronger the strong nuclear force gets. And in this case, we can see, looking at our little dials there, that while the electrical static force is pushing the protons away is quite strong, the strong nuclear force is even stronger. So it's going to overcome that repulsive force of the electrostatic force. But now if we start moving our protons away a little bit, as we look over here on the right side of the picture in B, we can see that as the protons move away, the electrical force is still quite strong, but now our strong nuclear force decreases greatly over distance. So now the protons are going to push each other apart. So as long as they're very close together, that strong nuclear force is going to be the strongest force and hold the atom together. So when we have a bunch of atoms, we can put them together. And if we have a substance that's composed of only one type of atom, then we call that an element. Okay? So for instance, if we have a tank of a gas and it's got all oxygen in the tank, it's just all oxygen atoms, then we would have the element oxygen. If you have a bar of solid gold, there's nothing but gold atoms in your bar, then you have the element gold. And when we look at all the elements in existence in the universe, more than 90% of the atoms in the universe are hydrogen, which was created in the Big Bang, so it's the most abundant element. The second most abundant is helium. And again, in the Big Bang, first there was this hydrogen. As stars formed and that immense pressure and heat was started in their cores, it could actually push the hydrogen atoms together and create helium atoms. And then as the pressure and heat increases, we can create heavier and heavier atoms. And almost all other elements were formed either in the cores of stars or in supernova explosions. We've identified 118 separate elements to date. And when we look around us, 91 of these occur in nature. The other 27 are produced by reactions in nuclear accelerators and nuclear reactors. And these 27 elements are very unstable. So they only exist for maybe a fraction of a second before they degrade into some other more stable element. So we consider those 91 are natural elements and then the other 27 unstable elements. And then when we look at the Earth itself, over 98% of all the matter on Earth is composed of only 8 of those 118 elements. When we look at the structure of the Earth, iron is the most common element. And you might think, well, I don't see that much iron in my everyday environment. But you have to remember that the core of the Earth, the molten core of the Earth, is almost completely iron. So the middle of the Earth is almost completely iron. Oxygen makes up another 30%. Then silicon is next, then magnesium, and then sulfur, nickel, calcium, and aluminum in smaller and smaller amounts. And so these 8 elements make up 98% of the world around us, of our Earth. When we're speaking of living organisms, whether it's bacteria or a tree or an insect or us or a dog, in living organisms, over 95% of weight is composed of only 4 elements. And those elements are carbon, hydrogen, oxygen, and nitrogen. And out of these 4 elements, you can make uh, lipids, you can make proteins, you can make carbohydrates. So you can make the tissues of our body out of mainly just these 4 elements. Atoms and elements are classified by the number of protons in their nucleus. Remember that positively charged proton in the nucleus. And the number of protons tells us A, which element it is, and also gives us its atomic number. So let's think back to hydrogen, that most common element in our universe. Hydrogen is an atom with just 1 proton, so its atomic number is 1. If we have an atom with 2 protons, well, now we know it's a different element. It's not hydrogen, it's helium. Helium has 2 protons in its nucleus, and its atomic number is 2. Moving up, we have our next element, which is lithium, has 3 protons in its nucleus. So what would its atomic number be? And of course, its atomic number would be 3. Elements can also be classified by their electrical properties, which is given to them mainly by the electron shells, that how many electrons it has in its outer shells. And when we look at atoms, we can see that the electrons are arranged in clouds or shells surrounding the nucleus. Some of the electrons orbit a little more closely on an inner shell, closer to the nucleus. Some of them are in outer shells outside that inner shell. And atoms can have several different shells. And each shell has a maximum of how many electrons it can hold. For instance, the first shell of an atom can have 2 electrons. The second shell can have up to 8 electrons. The third shell up to 18 electrons. And the outer shell of an atom is known as the valence shell. And this valence shell is what allows the atom to interact with other atoms. So most of the chemical reactions we see are due to reactions of the valence shells of different atoms. So we can arrange our atoms on our periodic table of the elements. And so you can see up top we have group, and the numbers go 1, 2, 3, 4, 5, 6, 7, 8, etc. And that's basically counting our protons. So as we move to the right, our atoms have more protons. We can also arrange them by period going down, and this is basically telling us how many electron shells does this atom have. So as we go to the right, more protons. As we go down, more electron shells. We can also classify atoms by their sizes, and different atoms are different sizes. And so, and mainly because the nucleus of an atom is so small and the atom is mostly empty space, what determines the size of the atom is the size of the electron shell. And what determines the size of that electron shell is what kind of charge and how much charge does our nucleus have, rather. So as we increase the charge in the nucleus by adding protons, we increase the positive charge. Then we're going to increase the amount of electrons in the outer orbits that have a negative charge. And again, you might remember from earlier science classes, what happens when we have a positive and negative charge? Well, they attract each other. So as we increase these opposite charges, the atom actually condenses, it gets smaller. So as we move from left to right in the periodic table and we add protons, the atoms are going to get smaller because there's increased electrostatic attraction between the nucleus and the electron shell. And so we can see here's the relative sizes of atoms if we could actually put them by size on the periodic table. And you can see as we go to the right, the atoms start to get a little larger. And also they get larger as we go, as we go to the right, they get smaller. They get larger as we go down because we're adding electron shells. But again, as we go to the right, we're adding charges. The charges are getting greater and more attractive. So the atom's actually going to get smaller in size. Most of our atoms have equal numbers of protons and electrons, and we call those neutral atoms because their negative charge and their positive charges cancel each other out. But some atoms don't. Some atoms have lost an electron, so they've gained a positive charge, or they've gained an electron, so they've gained a negative charge. And these atoms are called ions. And if our atom has lost an electron and gained a positive charge, we call it a cation. And if it's gained an electron and gained a negative charge, we call it an anion. Also, when we look at our atoms, we see that sometimes atoms of the same element don't have the same number of neutrons in them. Most atoms have, if you have an atom with, say, 2 protons, it'll have 2 neutrons. And some don't, though. Some have unequal numbers of protons and neutrons. And we call these isotopes. So let's look at hydrogen here. On the left picture, we see a hydrogen atom with just 1 proton and 1 electron, but no neutrons. And we call that protium. In the next picture, in the middle picture, we have a hydrogen atom that has a proton, 1 neutron, and 1 electron. And we call that deuterium. And then in the last picture on the right, we have a hydrogen atom. It still only has 1 proton, so all these are still hydrogen because they only have 1 proton. But now this atom has 2 neutrons, and so we call that tritium. And again, if we have a different number of neutrons, we call that an isotope. And isotopes can be really important when we're looking at the physical and nuclear capabilities of an atom. Our isotopes are identified by their mass number. And a mass number is just when we add up the number of protons and neutrons. So for instance, we can look at carbon atoms, and carbon comes in a lot of different isotopes. Now, all carbon atoms are going to have 6 protons. That's what makes them a carbon atom, is that 6 protons. But when you look at carbon, you might see a wide range of neutrons. For instance, carbon-12 has 6 protons and 6 neutrons. And we identify it again by that mass number, so we just add those protons and neutrons together, and 6 plus 6 gives us 12. So we have carbon-12. We might have 6 protons and then 7 neutrons, so that would be carbon-13. Or 6 protons and 8 neutrons, which would be carbon-14. It's important to remember that our isotopes have the same chemical properties as other atoms of the same element. Okay? So they have the same number of protons, which means they're the same element, and they have the same number of electrons, so they're going to react chemically the same way. But their physical and nuclear properties can be very, very different. Some isotopes of elements are what we call radioactive, which means the nucleus will actually undergo decay and emit radiation. Some isotopes are stable and they're not known to decay. They'll stay the way they are for millions of billions of years. And you can think of elements such as, say, uranium. Uranium has many different isotopes. Some are radioactive that undergo decay, so we can use those in medical applications and also to create nuclear energy. Some isotopes of uranium are stable and they don't decay, so they're not very useful in, say, nuclear medicine or creating nuclear energy. Sometimes we'll want to know the total mass of an atom, and this is where we not only count the protons and neutrons, but also the electrons. And if we add up all these particles and their weight, we get an atomic mass unit. Okay? And 1 AMU is equal to about 1/12 of the mass of a carbon-12 atom. The atomic mass for each element is the average mass for all those isotopes of an element. So when you look at the atomic mass number, it's usually not a whole number. So remember I talked about uranium has several isotopes. So we would add all those isotopes together, divide by the number of isotopes, and we'll probably get a number that's a decimal or it contains a fraction. Think back when we had carbon 12 and carbon 13 and carbon 14. So if we wanted to know the atomic mass for carbon, we'd have to add up all those different isotopes and get the average mass. Now that's a lot of different terms, and it's sometimes hard to keep them straight when we're talking about atoms. But let's go over them one more time. So the atomic number is the number of protons that we have in the nucleus of an atom. The atomic mass is the average mass of the atoms of an element. The mass number is the sum of the protons and neutrons in the nucleus. And then we have ions and isotopes. An ion is an atom that's lost or gained an electron. So it's going to have different chemical properties than other atoms of that element. An isotope is an atom that has the same number of protons but different numbers of neutrons. So now this atom might have different physical and nuclear properties. And of course, we rarely find atoms just wandering around by themselves. Usually atoms bond together with other atoms. And these atoms, when they're bound together, are called molecules. For instance, oxygen is most commonly found on Earth as two oxygen atoms bound together, as we see in the left-hand picture, and we call that O2. That's usually how we find oxygen. Some other common atoms we might encounter are, for instance, some nitrogen and hydrogen atoms together, which makes ammonia, some carbon and some hydrogen atoms together, which make methane, or an oxygen atom and two hydrogen atoms together, which form water. And all these are molecules, just different atoms bonded together. Now, some molecules are not the same element like our O2. Some atoms are different elements bonded together, like water is oxygen and hydrogen. And we call these compounds if it's atoms of different elements together. And these compounds can have characteristics very, very different from the elements that make them up. Let's look again at water. So with water, we have two hydrogen atoms, and hydrogen at room temperature is a gas. And we have one oxygen atom. Again, oxygen at room temperature is a gas. But yet when we combine these together, we get water, which is a liquid at room temperature. Okay, so it has properties very different from either hydrogen or oxygen. Let's look at these two elements. Sodium is an alkaline metal that reacts very violently with water. Chlorine is a halogen gas that, if we inhale it, is very poisonous. So these are not something that you would want to ingest or have on your skin, right? Neither sodium or chlorine. It'd be a very bad day for you. But if we combine these together, we get ordinary table salt, which is something that we put on our food and ingest every day with no harm to ourselves. So table salt has characteristics very, very different from either sodium or chlorine, the elements that make it up. In some cases, we can have atoms that are mixed together, but they're not chemically bonded or reacting with each other. So think of the air in your room that you're breathing right now. That air is a mixture of oxygen, nitrogen, and several other gases. But these atoms aren't really bonding or reacting with each other except for random collisions. So we call that a mixture. And a way to think of a mixture is think of when you've been to the beach, and if you reach down and you pick up a handful of sand and you look at it really closely, The sand is a mixture of little bits of ground up shells, and there might be some quartz or some sandstone that's broken up into little particles. But the different components of that sand are not chemically bound to each other. We could, if you had the patience and the time, you could actually separate every ingredient of sand out to, okay, here's some quartz, here's some little granite particles, here's some little shell particles, and you could separate it out because it's a mixture. It's not chemically bound to it. They're not chemically bound to each other. So when we talk about molecules, it's important to remember all compounds are molecules, but not all molecules are compounds. Remember, compounds are atoms of different elements bonded together, but molecules can either be these compounds of different elements, or molecules can be atoms of the same element bound together. Remember, we talked about oxygen usually being found as O2, two oxygen molecules together. So how are these atoms actually sticking together? And there's two common ways that atoms stick together. The first is with an ionic bond. And remember we talked about valence shells. Sometimes that outer valence shell is not full, but atoms want their valence shells to be full. So whether it's a shell that requires 8 electrons or 18, the atom wants its valence shell to be full. And so when we have two atoms that have valence shells that are incomplete come close to each other, a lot of times they will stick together. So let's look at our sodium and chlorine atoms here. In this case, sodium only has 1 electron in its valence shell, which is what makes it so chemically unstable. Chlorine is only missing 1 electron from its valence shell, which also makes it rather unstable and wants it. So both of these atoms like to react with other atoms. And if we put them together, we can see that the chlorine atom kind of, air quotes here, steals the extra electron from the sodium atom, and that is going to hook those atoms together. So you can see now, when we look at the molecule, the sodium atom has basically lost its outer valence shell, and the chlorine atom has actually completed its valence shell. So now they both have complete valence shells. We can also have covalent bonds, which is where instead of one atom taking an electron from the valence shell of another, they're going to share those electrons. So let's look at, say, these two hydrogen atoms up here, and they each have 1 electron. And when they run into each other, they want their valence shell to be full. They want it to have 2 electrons. So they both say, well, here, we'll share these 2 electrons. Now we both have 2 electrons and they're happy atoms. Same thing down here with carbon dioxide. We have our carbon atom here, and it's sharing electrons with 2 oxygen atoms. So they're very happy to share those electrons, and they're stuck together that way. Now, when we have these molecules that are of atoms sticking together, we can also break these molecules apart. But this requires energy. So think of our plants. So your plant usually just needs sunlight and then water and carbon dioxide. And the plants use the energy from the sunlight to break apart the bonds of water, the H2O, and carbon dioxide, CO2, to form carbohydrate. And they rearrange those atoms to form carbohydrates. And then they have oxygen as waste product, which they release. And we call these kind of breaking apart or putting together molecules chemical reactions. And this is any process in which we take atoms and rearrange them to form different molecules. So instead of having water, our plant now has a carbohydrate. So we need energy to break molecules apart, but if we combine atoms, that's going to release energy. So think about fire. And what happens when something's on fire? Basically, we're combining hydrocarbons with oxygen, and we call that process oxidation, and that releases heat. And so we can see here in our flames that maybe there's some wood or some paper burning, and it's creating, it's releasing heat as the oxygen combines with the hydrocarbons in the paper. This also happens when, say, iron rusts. When we leave iron out in the elements, it's going to combine with oxygen and create that oxidation that creates rust. This process also releases heat, but because it's kind of a slower process, we really can't say put our hand on it and feel that heat. But there is heat being released as iron rusts. So now that we know a little bit about atoms and how they stick together, we can look at what matter actually is and how it exists in various states. And some scientists will look at different states of matter, and some say there's 12 states of matter, some say there's 18 states of matter. But for everyday life and for our purposes, we're just going to talk about the four most common states of matter: solid, liquid, gas, and plasma. So when we're talking about something that's a solid, we're talking about some matter that has a defined volume and a defined shape. So think of anything that's solid, whether it's your coffee cup or a ring on your finger. It doesn't change volume and it doesn't change shape very easily. You would have to exert some type of force on it to change its shape. The atoms, if we look at them in a solid, are very close together and they're relatively fixed in place, so they can't move around freely. But again, all atoms are moving, at least vibrating in place. So in solids, our atoms are vibrating in place. When we're discussing liquids, now we're talking about a matter that has a defined volume. So if you have a liter of water, you have that volume of water. You can't compress or expand it. But it has a variable shape, unlike our solids. So liquids are going to conform to whatever container we pour them in. So if we have a liter of water, we can pour it into a shallow bowl and it'll spread out. We can pour it into a really tall tubular vase and it will conform to that structure. We can pour it into a round fish bowl and it will conform to that shape. So, but we still have a liter of water. We still have the same volume, but the shape can change. And if we look at the atoms in a liquid, they're relatively close together, but they're not fixed as they are in solids. So they can move over each other very freely. When we move to gases, now we have matter that has both a variable shape, but also variable volume. We can compress or expand gases, whereas with liquids, it's much more difficult. We can't do that. Like liquids, gases will conform to a container. So you can blow up a balloon, and so the gas is going to conform to the shape of a balloon. We can put, say, oxygen into a scuba diving tank, and it's going to conform to the shape of the tank. We can also, so as we're changing its shape, we can also change its volume, though. So we can compress gases, and we can get a much greater volume of gas, say, into a scuba tank than is just floating around in the room. The atoms in a gas are not very close together, and they're not fixed at all. Usually in gases, the atoms don't react with each other at all unless there's just some random collisions going on. When we have plasma, this is a rather different state of matter. So it has variable volume and variable shape like gases, but the difference here is that the atoms in a plasma have their electrons disassociated from the nuclei. So in a plasma, basically we have what's called almost like an electron sea, that all these electrons are just floating in the cloud together. And the nuclei are just kind of floating in this electron sea. So, but unlike in solids, liquids, or gases, we can't say, okay, this electron belongs to this nucleus. We usually only see plasmas in when we pass, say, very strong electrical charges through a gas. And if we look at our states of matter, remember to break some of these bonds, we have to add energy. Like our plants use the energy of the sun to break chemical bonds between atoms. So let's look at our states of matter. So we can have a solid. The atoms are fixed in place, just vibrating in place. In a liquid, they're loosely bound so they can roll over each other. In a gas, they move freely, they don't interact with each other. And then in a plasma, again, our electrons are dissociated from the nucleus. And we can see this going, we can do this at home. So you can take, say, some ice out of your freezer, and that is H2O, water, and it's a solid. And then if we add energy as heat, say we put that ice in a pan and put it on the stove, add heat, it melts and becomes water, a liquid. If we keep adding heat, it will turn to steam, a gas. And then if we could keep adding heat or energy, at some point we could turn that water into a plasma. But we have to have energy to change it from one state to the other. So when we look at matter, we know that we have positively charged nuclei because our protons are there with that positive charge, and we have negatively charged electrons. And as far as we knew, all atoms in the universe were like this: positively charged nuclei, protons, and negatively charged electrons. Well, in 1931, there were some strange particles called positrons that were discovered by researchers. And these positrons were actually electrons that had a positive charge. So, opposite from what we thought matter had to be. As scientists have experimented in nuclear accelerators, they have managed to produce what we call antiparticles, which are particles that have the same mass as regular particles, but an opposite charge. So we can have antiprotons, which have a negative charge. We can have antineutrons, and then positrons, which are electrons that have a positive charge instead of the negative charge. And we call all these antiparticles antimatter. So we know antimatter exists because we have created and looked at these negatively charged nucleons, or protons rather, and positively charged electrons. And antimatter has the exact same properties as matter aside from its charge. So if we had a star that was made out of antimatter and we're looking at it through a telescope, there's no way we could tell the difference. It would shine and behave just like an ordinary star. The only difference is in the charges of its subatomic particles. So what would happen if matter and antimatter came in contact? Say that a meteor made of antimatter came into Earth's atmosphere. Well, what would happen was equal amounts of each would be instantly converted to energy. So the antimatter meteor would instantly be converted to energy, and an equal amount of Earth's atmosphere would be converted to energy. And this is what actually happened when scientists created the first artificial anti-atom in 1995. It instantly came in contact with an atom of matter, and poof, they were both gone in a burst of energy. Scientists have also discovered other weird types of matter. When scientists were studying the gravitational forces within galaxies, they noticed that we're seeing more gravitational forces than can be accounted for by the matter that's actually in this galaxy. So scientists posited the existence of dark matter, which is matter that we can't see and to date is unidentified. And scientists estimate that this dark matter that we are really ignorant about comprises about 23% or almost a quarter of the universe. And dark matter, if we can ever find it and study it, is probably going to be very different from the elements we are familiar with now. There's also a force called dark energy. If we have dark matter, we probably have dark energy as well. And this is the unknown force that's actually pushing outward on the universe. We can tell by looking at Doppler shifts that the universe is expanding. And we could not figure out why until scientists also hypothesized that there's this dark energy. And as far as we know, dark energy does not interact with matter um, with any other force but gravity. And dark matter and dark energy are thought to make up about 96% of our universe. So we're actually living in a universe in which most of it we are unaware of.